Well, we want you all to know that we're now being broadcast globally on live webcast. So, Wally, you're going to have international distribution. Wally is best known, perhaps, for having a knack for tackling particularly difficult and vexing and, most of all, big and large problems, and then solving them, and then able to get them out into print within the time scale of weeks. He has, we actually just celebrated Wally's, well, I can say it, his 70th birthday last week, and so Wally's been feted now for on the order of about 10 days, so he should be softened up well for this talk. He's, when it comes to writing, Wally is really not a slacker at all. He's had about 411 papers that I know of so far over the last 40 years. It's an average productivity of 10 per year, which is a heck of a lot better than I'm doing. But when it comes to science, Wally's perhaps best known for his generosity. He's someone who's influenced probably the career of every single person in this room, and he is particularly generous toward junior scientists and really giving them a lending hand and advice when they need it most. Wally's no stranger to awards. His secretary, Moana, gave me a list of his awards, and I won't go through to read them, but he's basically won them all. Perhaps the most important one to him, though, is the Oak Park River Forest High School's Tradition of Excellence Award. So aside from the National Medal of Science, that's the number one. So it's an honor to be your colleague, Wally, and it's your show.
I don't give PowerPoint presentations. As you know, I'm a pencil point person. So this is a very interesting picture. Jim White pointed out what he's doing. Those were the old days when you had strip charts and the isotope measurements came out as peaks instead of in the computer. And he has got those charts there, and he's drawing the tops of the peaks and measuring the differences. That was the hard way. Cesare, I mean, if there's ever a scientist who made his reputation, and very deservedly so, on a single paper, it's he. He did the first oxygen isotope measurements in the early 50s and published a paper in, I think, Journal of Geology, if I'm not incorrect, at about 1955. And I would say that that's the classic paper in the field that I work in paleoceanography. It remains an extraordinarily important contribution. Now, Cesare, as he aged, changed. He called me up twice at about midnight. I go to bed early, and my wife both times said, there's some crazy Italian on the phone. He insists he has to talk to you right now. It's very important. The first time, he was totally blown out over the fact that the year 0 is not in the calendar. It went from -1 to +1. There's no year 0. So he wanted to redo the whole calendar, and he said, to hell with this, you know, basing it on the life of Christ. He wanted to put 0 year at the end of the Younger Dryas. And then about a year later, this is probably a couple of years before he died, he called me up again very late at night and said that he was forming an organization that he wanted me to join. It was the Golden Something, but basically it was the Golden Oldies. And he was very upset that young professors were making too many decisions in universities and it should be done by wise old men like us. And I thought, holy Christ, what a disaster that would be. Anyway, he was a character. It's nice to have people like that to remember. Okay, I've for a long time been interested in carbonate dissolution. I wrote a paper in 1972 that I think for the first time pointed out that the depth of the transition zone from carbonate-rich sediments in mid-depths to carbonate devoid sediments at great depths was controlled by economics and not by temperature and productivity and things that other people had pointed out. The point was that the carbonate system in the ocean, there was an overproduction of perhaps a factor of 4 in calcite compared to the ingredients coming in, so the ocean had to do something to get back this overproduction. So it set the level of this transition zone such that the appropriate amount of calcium carbonate fell into deep enough water that it would dissolve. And Taro Takahashi and I fiddled around with things related to this over the years. And recently, I sort of stumbled on, I started measuring the ratio of coarse calcium carbonate to total calcium carbonate and found that for the Holocene, there was a beautiful correlation, at least in tropical sediments, and I thought maybe I could use that to go back into the past. Well, I encountered Pat Lohman here a couple of years ago, and he said, Wally, that's never going to work. He said, why don't you start to use my method, which was a method based on the weights of formin for the thickness of their shells. And he was right. When I tried to apply my method to glacial, it fell apart. The assumptions failed. And so I switched over and have been working for a year and a half with Elizabeth Clark, who's here, but I know she prefers to remain anonymous, so I won't ask her to stand up, or I'll pay the price later on. But Elizabeth and I are a great team. She picks and weighs, I write. So anyway, now up until a week ago, I really didn't have a good story to tell, and I said, here, I'm going to maybe fill up this room and then give a boring talk. But in Utah, I was at a meeting on CO2 run by Turi Serling and Jim Elringer, and I woke up at 3 o'clock in the morning, I think, last Friday, and I couldn't go back to sleep, so I thought I'd do something useful, and I started to think, and I thought about what this data I have, that Elizabeth and I have, really meant, and I came up with a very interesting idea. Now, that I warn you, this idea is only, 5 days old, 4 days old. Fred Hoyle gave a lecture at Columbia when I was a graduate student, and he pointed out that a quack is a person who gets ideas and never criticizes any of them, keeps them all, good and bad. He said there are other scientists that are so critical that they never let an idea germinate, and they get rid of it because they find things that are wrong with it before they've thought it through. He said a good scientist gets an idea and nourishes it, like letting seed grow a little bit. And when it's well in his mind, only then does he turn the blast of criticism. I think I'm just starting to turn the blast of criticism on this idea, but it's an interesting one, whether it's right or wrong. Now, what I mean by water mass wars is the fight for space between North Atlantic deep water, which is mainly produced in the North Atlantic, but has a sizable mixture of water from the Southern Ocean, and the rest of the world ocean water, which at least today is about 50-50 mixture of water that descends in the North Atlantic and water that descends in the Southern Ocean. So the mean ocean is something like 60-40, if you average them together. And I'll show you something about the interface in a couple of minutes, but I think what I'm seeing in this data is the interface swinging back and forth following Milankovitch cycles. So if correct, it's very interesting. Now I started out and I wanted to do two things. I wanted to know how the glacial to interglacial carbonate ion distribution in the ocean changed. So we'd say these ambient periods that are somewhat constant climate, although not really. So this is idealized. The other thing of interest, and this is what I'm going to talk about today, is that there were two reasons why you might expect carbonate preservation events at the beginning of interglacials and carbonate dissolution events at the beginning of glacials. One is that if the C13 data and explanation thereof are correct, there was a greater terrestrial biomass during interglacials and glacials. So when you built this biomass at the end of a glacial, you would extract CO2 from the ocean and raise the carbonate ion content and make a preservation event. On the other hand, if you destroyed that biomass at the end of an interglacial, you would put that CO2 in the ocean and you destroy carbonate ion. Now, as a number of us have shown, the amount of carbonate ion in the ocean is quite small, and if the system is thrown out of balance so that burial exceeds supply or supply exceeds burial, the ocean will adjust on the time scale of 5,000 or so years. Eric Sundquist has written papers about this. Taro and I have written papers about it. So it's a fast adjusting system. Now, but just a quick review of things. All of you have seen the fact that if you're shallow in the ocean on ridges and plateaus, thank you, the carbonate content of sediments can be up between 85 and 95%. And if you go deep enough, it drops to 0. And there's a transition zone. I hate the terms lysocline and compensation depth. I prefer to just say that since their boundaries are poorly defined, that there's just a transition zone where dissolution gets strong enough to take away all the carbonate. The carbonate content is very deceiving because if you start with 90% carbonate and dissolve half of it, you've still got 80% carbonate, so that it's not very sensitive. And of course, you can have variations from place to place in the ratio of falling carbonate to falling debris. But anyway, that transition zone is related somehow to the saturation horizon for calcite. And I'm not sure how well we know where that is. It's somewhere down in this depth range. But there, as shown by Emerson and Hales and Archer, above that saturation horizon, dissolution is definitely occurring. Fred Sales and Bill Martin have shown this, Dan McCorkle, various ways to show it. It's clear that this is occurring. pH probes put into the sediment shows that there's a sizable drop in pH. If you convert that back to carbonate ion, it's a sizable drop in carbonate ion. So in the upper few centimeters of the sediment, respiration is acidifying the water and dissolving calcium carbonate well above the lysocline. Now, this is a big complication for what I'm going to try to do, because the evidence I'm going to use has to do with the calcite itself, and therefore a lot of this dissolution occurs in the pore waters, and one can always ask whether what we're seeing is a change in deep water or a change in the impact of this raining, of the raining organic material. So ideally, this respiration CO2 should always produce the same effect at every depth. Then, because the solubility of calcium carbonate increases with depth, well before you get to the crossover, where you could get inorganic dissolution on the bottom itself, the pore waters cross this curve and allow dissolution to take place. Now, fortunately, there are methods that don't depend on sediment base. I'm going to use the Lohmann method here mainly, the whole 4M shell weights, but of course that's affected by this pore water dissolution. Tom Marchito has shown that you can do the zinc-calcium ratio. Gary Hemming and my former student Sanyel showed that you could use boron isotopes to get the change in the water itself. There was a talk given at the Gordon conference that made boron isotopes look very bad. I would say that's nonsense. Boron isotopes is one of the most powerful techniques we have, but it's like boron isotopes are in the Emiliani days, very early on. After all, it took all of us brilliant people 40 years to find out that the oxygen isotope fractionation depended on carbonate ion, and so forth. So that the boron calibration curves are beautiful. The problem with boron isotopes is that there are offsets between species, and only a couple of them have been determined. These offsets are big, and if you can't find a way to correct for them, then in a sense you're in trouble, especially if you want to do benthic forams, which is what I would want to do to check to see how much of what I'm seeing is in the water rather than in the core water. Now, it's going to be important to just review quickly today's carbonate ion concentration distribution. And it's fortunately rather simple, so it won't take me long to explain it. And that is, it's amazingly that it's bimodal. Almost all the water in the Atlantic has a value within a few micromoles per kilogram of 112. And almost all the water elsewhere in the deep ocean has a value of, say, 85 plus or 83 plus or minus 6 or something. Fairly narrow range. Big difference between these two. So I'm going to use this difference to show how water mass wars work. So if this guy invades this guy, he's going to make a dissolution event. If this guy invades this guy, in a sense, he can make a preservation event. Now, if you look at the distribution on a map, I mean, the only place in the ocean where there's really a prominent gradient with depth in carbonate ion in the deep ocean is in the South Atlantic, where you go from North Atlantic deep water at shallower depths to Antarctic bottom water at deeper depths. And of course, there you see, when you measure carbonate ion, that you get a transition from North Atlantic deep water values to deep Pacific values. You may wonder why I put silica down here, because carbonate ion measurements are noisy. But if you plot them all against silica, there's a beautiful correlation in the South Atlantic. So if you want to get a smooth profile, it's better to use the silica data and the, statistical calibration between the two. Okay. Now, you might say, well, carbonate ion difference between the Atlantic and Pacific is just related to nutrients. That the more phosphorus you have in the water, the more respiration CO2 you have in the water. The more respiration CO2 you have, the lower the carbonate ion. And, well, that's true, but you would predict from the phosphorus difference that the difference in carbonate ion concentration between, say, deep waters in the tropical Pacific and tropical Atlantic should be 100 micromoles, and it's only 30. Well, Sung-Hoon Peng and I, a long time ago, when we were worried about the gradient of CO2 in the atmosphere, which is important in trying to understand the current carbon cycle, showed that something interesting is going on in the ocean. These high respiration CO2 waters in the Southern Ocean come to the surface, they lose CO2 to the air. That CO2 or its equivalent is taken up in the Northern Atlantic by new North Atlantic deep water. And this transfer, which is large, about 80 micromoles per kilogram, reduces this difference from 100 down to 30. So the difference is influenced by two things, the phosphorus content and this transfer of CO2 through the atmosphere. Okay. Now I call this luminology seriously because Pat did a really right thing. In 1995, he published a paper showing that this was probably the best way to go about measuring dissolution. It has a big advantage in that other methods often measure the ratio of one entity to another, and that always involves the question of were these entities produced in the same ratio in surface water, and can you actually make that assumption? Well, he's making a simpler assumption that all these given species of foraminifera form shells with the same average thickness, and this doesn't change with time, which it might. And therefore, if you look at the weight loss of a shell, you get a measure of how much it's dissolved. Now, the way Pat proposed to do this is to disaggregate the sediment, isolate the 63 micron fraction, clean it as well as you can without breaking up the poor forams, and then sieve in fairly narrow size fractions and he picked 75, Elizabeth picks about 50, pick 50, and then weigh all 50 and divide by 50, and that gives you the average weight of a shell. Now, the range of weight is bigger than you would expect from the size range, and I think that reflects the fact that forams in the bioturbated zone, some of them are lucky and they go right through. They don't lose much weight. Other ones wander around hopelessly for thousands of years and then go through, they lose more. But it turns out that the statistical error, just due to the fact we're not sampling the whole ensemble well enough, is about 2 micrograms. And you'll see that in the data, that an individual measurement has an error of about 2 micrograms. These forams weigh sort of like 30 micrograms. Okay. Now, as Pat showed, you can calibrate this method by taking cores that are in different carbonate ion concentrations and in different depths. And I chose to do it a somewhat different way than he did, and that is to create a pressure normalized carbonate ion concentration that takes into account the increase in solubility with pressure. And so these are a bunch of samples that Elizabeth measured from the Antang Java Plateau, from the Atlantic, Sarah Rise, and from the Caribbean. The numbers are the number of samples, because if you only measure one and you got this 2 or so microgram error, that's these black points are just single measurements, they show more scatter than when you do an average. So surprisingly, because it is surprising, this means the ocean is a lot simpler than you might think, these do fall along a line. These shells lose about 0.3 of a microgram per micromole per kilogram of pressure normalized calcium carbonate. You see the weight loss here goes from maybe 36 down to 22 or 3. You get down to somewhere around here, and they get very punky. And if you hit them with the ultrasound, they tend to break up. If you don't hit, even if you don't hit them with the ultrasound, they're broken up, and therefore you can't use this method unless you can get whole shells. So there's a limit. Now, we're getting toward the data here. One point that I've been emailing around trying to find out, I've been using the equivalent of the way they express this solubility increase is the difference in volume between the ions, calcium and carbonate in water and in the shell. Actually, they take up more room in the shell than they do dissolved in the water, and that's why the solubility goes up. There have been measurements as high as 43 and as low as 31, I think, estimates of this. I'm using something closer to 45. Probably have to change that and lower it. What that would do would mean that the actual sensitivity of the method goes up. Instead of 0.3 of a microgram per micromole, it might be 0.4, something like that. But what I have to say doesn't depend too much on the absolute calibration. Now, I'm interested in the glacial to interglacial differences in the ocean, but you got to remember that that's dictated by economics. So the question is not what the temperature of the water was or anything else. It's what, for the average ocean, it is a measure of the overproduction. So it's a ratio of the amount of calcite produced every year, or calcium carbonate produced every year, to the amount of ingredients that are coming into the ocean. And that ratio is somewhere around 4. I don't think we know it very well. There's a large overproduction. So if it were the same in the glacial, then the average depth of the transition zone wouldn't move. So the transition zone average depth tells us nothing interesting oceanographically. That's just mass balance, and the bank account of the ocean is being kept on a several thousand-year time scale. Now, I just show you this, surprising. This is my reconstruction, which appeared in Science this week or next week. Going to appear sometime, which shows an interesting thing, that unlike the present-day ocean, where you have constant carbonate ion with depth, except in this transition zone in the South Atlantic, and of course you have higher values in the Atlantic than the Pacific, it appears that there were gradients in both. Pat Lohman has a poster for tomorrow afternoon where he's done the same thing in the Atlantic, but he's done it on the eastern side of the ridge in the tropics, and I've done it on the Sierra Rise in the western side. So I'm not going to say any more about this. If people are interested, they can read the article in Science. I want to focus on preservation events and dissolution events, because this is where the big surprise comes in. So let's start with preservation events. Dan McCorkle was kind enough to share with me his I barely get it all on. Material from a suite of cores that he took on the Antang Java Plateau right on the equator. That's nice because the sedimentation rates are about twofold higher than off the equator. And I got detailed samples for the Holocene. So this is 3 Holocene records. You can see each one is radiocarbon dated. The red line is approximately at 9,500 years. Now, let's start with the deepest core. The deepest core has a profound preservation event, so that the weights of both P. oblique and G. sac have a maximum somewhere around 9,000, 9,500 years, and then coming up to present, they drop off until you hit the sediment bioturbated layer. So presumably, if this is still going on, these weights for what's falling today would be even less. Robin Keir recognized this about 18 years ago, I think, and wrote a paper about it. Nobody paid too much attention to it because this was sort of outrageous to believe that our constant Holocene was having a huge carbonate ion change. This 10 micrograms is equivalent to 30 micromoles. It's equivalent to the difference between the Atlantic and Pacific. It's not a small effect, it's a big effect. Then you go up to 3.43 kilometers, and the effect gets half as great, and it starts to look a little rattier because of our 2 microgram error. And then you go up to 2,300, and there's just no evidence of a trend. You could draw, it's a scatter of our measurements. So we have a preservation event in the Pacific, which is strongly depth dependent, and it says 9,000 years ago, the carbonate ion down here was 30 micromoles higher. Here perhaps was 10 to 15 micromoles higher, and here it was about the same. So the carbonate ion had a great gradient at that time, and it's relaxed until, by some miracle, it's almost straight up and down today. Okay, so now let's look at the Atlantic and see what's going on there. Well, here's a core at 3.2 kilometers. The red line is, again, about 9,500 years. And you see, again, like in the shallower Pacific, there's absolutely no evidence of a preservation event. If this terrestrial biomass was released and back and forth between glacial and interglacial, that should produce a measurable preservation event throughout the whole ocean. So I don't see any of that here. Okay, let's go down a little deeper in the Atlantic. Elizabeth did this core last week as a favor to me because I wanted to see whether there was any evidence at 3,700 meters on the Sierra Rise. We just did a few samples and haven't gotten radiocarbon dates, but the calcium carbonate content, which takes a huge drop in glacial period on the Sierra Rise, tells us it's about here. So it's pretty much all of the Holocene. And again, no gradient, so no preservation event. Earlier, we published a paper by our other method of ratio of fine carbonate to coarse carbonate, in a sense, which we attributed to the fact that as shells break up, the average size gets smaller and smaller, and so our size index, the smaller it was, the greater the extent of dissolution. So there's our two cores way down deep, 5,200 meters, 11 degrees north of the equator, and you see in both cores you get a tremendous peak in calcium carbonate, and which is again drawn by using the radiocarbon dates, is somewhere around 9,500 years, and also the size index peaks there and then drops off both ways. So there is a preservation event in the deepest Atlantic. We can't do shell weights here because there ain't no whole shells to weigh. I mean, they're all broken up. Okay, so that's preservation events. We're looking at the distribution of these at the end of the last glacial period. Now let's look at dissolution events. So these are the things that occur at the onset of a glaciation. And we did a series of cores provided to us by Bill Curry, and we found in each core, so this is at 2.8, 3.5, 4.0, that more or less at the beginning of stage 4, there is a profound dissolution event. At the deepest core, all the foraminifera are broken up. There's nothing for Elizabeth to weigh. Calcium carbonate content takes a big dip because a lot of it's been dissolved. Shallower, you still have some intervals where there's not enough to weigh, but you can see that there's a dip in weight. And even up here at 2.8, there's a dip. So in this case, we see the event all the way up. We even see it in the Caribbean core, which represents water spilling over the at 1,800 meters, so it'd be upper glacial deep water. So here we're seeing that the dissolution events don't look in distribution like the preservation events. I asked Bill to give me some material to look more carefully at the end of stage 5A, and there's a second dissolution event there that's very strong. And you see in this particular core, there weren't any forams to weigh in that layer, and there's a big drop in calcium carbonate, which is almost certainly dissolution. Okay, so now let's move over to the Pacific, and we're almost got the job done. And here I'm not sure. Here's that core from 2.3 kilometers. You get some sense that there isn't much glacial interglacial change, or at least you wouldn't believe any measurement. There's one measurement, I don't know if we made that early or not, but anyway, and down here at the beginning of stage 4, there's some indication of a dissolution event. The calcium carbonate, my index drops off, the calcium carbonate drops a hair, and these weights. But compared to the Atlantic, it's not as big. So that's strange. Now, Bob Anderson encouraged me at one time. He's standing way in the back. I thought I saw him. Hello, Bob. You can come in. You don't have to stay outside. This is a core from 140 west, and you see here that there may be some evidence of a dissolution event where it should be. So I've mainly drawn this because that's where we'd expect it. But the changes in weights aren't too impressive, and there is one level where there's insufficient shell. So I'd say maybe we should do more on this, that the dissolution event is probably present in the Pacific, but I think weaker than it is in the Atlantic. Now, so let's summarize, and then I'll give you my 3 o'clock in the morning thoughts. Preservation events are in the abyssal ocean only, so you have to go very deep to see them. If you get up in mid-water column, can't find them. You should be able to from our calibration curves. The dissolution events, on the other hand, appear to be water column up and down, wide in the Atlantic, but weaker in the Pacific, with some caveat that maybe we should do more in the Pacific. Okay, so here's my idea now. It's all on one slide, and that is that these dissolution events and preservation events go along with northern hemisphere summer insolation curves. And so we have the peak of this preservation event in the deep Atlantic and Pacific is just a little bit after the peak of the summer insolation, shown here in red, roughly, termination 1, but so somewhere around in here is the peak of the insolation. And back here, we have a preservation event just after termination 2, a strong dissolution event. I see some evidence for another pair here, but it's really not been worked out enough to say for sure. And then the pronounced dissolution event that I've been showing you in the Atlantic. So what could explain this? Well, what I think is happening is that during times of strong northern hemisphere summer insolation, North Atlantic deep water and interglacials is denser for some reason. You know, you can argue it should be less dense, more dense. I'm just going to say it was more dense, because if it were, then I can explain this data. If it wasn't, then of course this is nonsense. And then during the insolation minima, North Atlantic deep water was less dense. Now, of course, at the other end of the globe, you've got the flip side of this. The insolation 20,000-year cycles are inverse, so the Southern Ocean is seeing the opposite. So I'm saying it would be strange with these two water masses fighting for position in the ocean if they didn't recognize Milankovitch cycles. These are sizable changes that are giving first the North Atlantic higher radiation and then the Southern Ocean higher radiation. So now, how do I explain the geometry? Well, if you make during these events North Atlantic deep water more dense, it can do an interesting thing. Those of you like Robbie Togweiler over there know that North Atlantic deep water, when it goes around Africa, it does so what's centered at 3 kilometers or something. It's fairly high up in the water column because it's less dense than the deep waters in the Southern Ocean. But if you made the North Atlantic deep water more dense, or if you made, let's stick with the North Atlantic deep water, then that water, if you got it dense enough, would tend to be more dense than the waters in the Antarctic, and that would move down and it would penetrate around Africa at deeper depths. So what I'm saying is happening is that during these times, the reason you get preservation events is because North Atlantic deep water is doing two things. It's shoving back Antarctic bottom water, and that's why you see the preservation event at 5,200 meters in the Atlantic. And you see the preservation event in the Pacific because this water is coming around stronger and deeper, and it's doing the job. Now, then you say, well, that explains the preservation events. How do you explain the dissolution events? Well, I would say when the density of North Atlantic deep water gets weaker, the percentage of other ocean deep water that gets into the Atlantic, it's now 20%. It's surprisingly uniform. North Atlantic deep water doesn't show a big gradient in the contribution from southern waters. It's pretty much 20% plus or minus 5%, something like that. Well, perhaps what happened for these dissolution events is that when you weaken the density, lower the density of North Atlantic deep water, then the other water comes in and produces dissolution events at all depths in the Atlantic. So to summarize then, in my quest, I wanted to understand whether there were dissolution events or not, and I wanted to try to use the amplitude of these events to distinguish between how much was Archer-Meyer-Reimer, which is a proposal to explain glacial CO2 by putting even more respiration CO2 in sediments. I won't bore you with details of that. And this forest thing. And when I started to get these results, it didn't really make sense because the geometry of the distribution wasn't what I would have expected. And so perhaps we're seeing a whole new phenomena here, that the water wars are going on, and it reflects a change in perhaps salinity in North Atlantic deep water, gets more saline when you have strong insulation. I don't know, various things. Now, you could say, well, Curry and Shackleton and others showed that benthic forams were 0.35 per mil, or they suggested a 0.35 per mil lower delta C13 in deep water during glacial time. And the easiest way to explain that is to do this biomass change. And I would say if they're right and the biomass change was that big, I should see dissolution events at places, and preservation events, places that don't see them. So one might say, well, how do you explain that? I was just at a meeting in Utah where people are obsessed with C3 and C4 plants and how they change. And apparently, Joe Barry and others are saying that on our planet today, there's about 25% of the photosynthesis is by C4 plants. And they would say by theory that during the glacial period, it may be as high as 60%. So one way to get this 0.35 per mil shift is just to have a planet that had more of its terrestrial biomass stored in C4 material, which has a smaller fractionation, and less in C3 material. So that's an explanation. But that'll be an interesting thing to chase down because there is a seeming disagreement between what we would expect and what we see. So I hope that was painless. I try to keep it reasonably short. I'm glad to try to answer questions, or I asked Bill Curry, maybe he could shoot the whole thing down and we could be done with it. Thank you.